Okay, so welcome to Emergence Data Matter lecture number 2. So just a couple of quick announcements. So next week I will be out of town, so the lectures will be on video and I will send you the details later. The office hour is most likely to be Tuesday 11 in my office in Uri Hall 7262, and then any other time you want, either by appointment or just texting me on Teams or however you want to do it. So 24/7 on Teams, physical office hour, most likely to be there. Okay, so now for the rest of the quarter, the lectures are pretty much mostly going to be written on the screen like this, so not PowerPoint. I want to start off by recapping the most important things that we discussed in our first lecture. So the first thing is that we discussed why emergence was important. We talked about levels of description. We talked about the task of condensed matter physics, and that's highlighted in the picture at the bottom of the screen. So what you can see there is we had this picture of the macroscopic world being informed and reflecting properties of the microscopic world through phenomenological parameters. And of course, there are multiple microscopic models of reality that correspond to the same macroscopic picture. So you may, for example, have thermodynamics as your macroscopic picture of the world. And then that seems to apply to virtually everything in equilibrium, at least, or near equilibrium, and there's extensions of it. But then you can start to drill down, and even if you don't know that atoms exist, you can still make thermodynamics. You can then use thermodynamics and statistical physics to actually explain why atoms should occur and predict what the outcomes are. And you can have many different theories of what the fundamental world is. What is the gauge group of high energy physics, the standard model of particle physics? There are multiple different versions of that, all of which will give you the same atomic physics, all of which will give you the same chemistry, all of which will give you the same condensed matter physics, all of which will give you, many other macroscopic phenomena that we observe. So I've written out schematically as micro 1, micro 2, micro 3, and the task of, and then going down even to further levels of description, nano, and so on and so forth. And the task of fundamental physics is to try to deduce what the rules are for the actual universe that we live in. And that's difficult because the task, as we go down in scale, as we go down in energy, as we go up in energy, as we go down in length scale and time scale, that map is one to many. What I've called emergent physics is where we go the other way. We start off with a level of description which is microscopic, say the atomic level of description, and then we try to deduce what are the macroscopic properties of the material that we see. So fundamental physics is hard because, and this 3 dot symbol means because, the fundamental physics is hard because the map from macro to micro to nano, etc., is one to many. Emergent physics is hard because new collective phenomena arise when one groups together high energy, fast, and small length scales, length and time scales together. So we take degrees of freedom, which have high energy, have fast time scales, have small length scales. We try to group them together into more macroscopic variables, and those are low energy, have slow time scales, and have large length scales. And so you might think, for example, of the atoms in this room, in the gas that you can hear me talking through. So ultimately, it's particles bouncing around in the box, but you can hear me because there's a continuum description on much larger scales, which is of a density and pressure, and you can hear me because I'm exciting density and pressure waves by talking, and those are propagating, and those you can hear. And so emergent physics is hard because we are going from these high energy, fast, and small degrees of freedom to low, slow, and large degrees of freedom. And we call that process coarse graining. This process of going from those scales, we call that coarse graining, and that is an important ingredient of the renormalization group description of physical phenomena. And that's going to play a large part in what we do in this course. Coarse graining is not the only thing that is part of the renormalization group, but historically it was the realization that one can do this, and that one should do this, and that your description of matter, description of science and physics and chemistry, biology, etc., depends on the scale. That realization was really first made by Leo Kadanoff in 1966. And so the process of coarse graining was first epitomized by Kadanoff's construction, which is called the Kadanoff block spin construction. And we will talk about that during this course. Now, at the end of the course, at the end of last lecture, we talked about scaling laws. And so we talked about the following phenomenon. We think of a magnet as being made up of a bunch of magnetic dipoles that can either point in the up direction or the down direction. And we measure the magnetization per spin, which is the fraction of spins that are up minus the fraction of spins that are down in some coordinate system. And we think of this spins as being on a lattice, having a spin variable which we'll write as plus or minus 1, and they can be in an external magnetic field. Now, the phenomenon that we're interested in, the emergent phenomena, is shown in the picture on the left in the graph. What you're seeing there is the magnetization as a function of temperature. And if you take a bunch of spins and just put them at high temperature, entropy just makes them fluctuate up and down. And if you measure how many spins are up, it's the same as how many spins are down. And so the magnetization is 0. But the amazing thing is that as you go down to low temperatures, suddenly more spins point up direction than in the down direction. Or it could be more spins point in the down direction than the up direction. That's the emergent phenomena. And the point where that happens is the phase transition phenomena, and that's the temperature Tc. And the question that we're going to be asking in this course is the following. If I look very close to the critical temperature, to the point where the phase transition occurs, what is the behavior of the magnetization as it grows slowly from 0, as you can see in this sketch over here? And at the end, I gave you a challenge. Let's make a theory of this, and I only gave you 10 seconds to make the theory. And I gave you, in fact, a minute. But the way we actually constructed the 10-second theory of this was as follows. We simply said, let's take this graph and let's turn it on its side, 90 degrees. So I've got temperature now as a function of the magnetization rather than magnetization as a function of temperature. Now, the spins can point either up or down equally well. So this curve over here is symmetrical. And so then I said, well, if we expand the temperature as a function of the magnetization close to Tc, then that should have the following form. Let's make this thing go away. What I really want is, why can't I see my colors? What I really want is this. So what I really want to do then is make an expansion of the temperature around that. So that we'll say it's going to be Tc, and it's a curve that's pointing down. It has to be even, so the first term has to be m squared. There are higher order terms that have to be m to the 4th. And so that immediately tells you that very close to Tc, just rearranging that equation, m should go as Tc minus T to the power 1/2. Or more generally, we can say that m scales as the temperature, the reduced temperature, with an exponent of 1/2. So that's the picture, and we say m scales with reduced temperature. And when I talk about the reduced temperature, that's defined by this. That's the reduced temperature. Okay, so that is our picture, and that's our prediction. And it only took us 10 seconds to make that prediction, but unfortunately, it's completely wrong. Okay, we know this for sure. Okay, it took a long time for people to be able to do the experiments to really show this, and then to be able to work out computer simulations. But we know that experimentally, this exponent beta is actually not a half at all. It's 0.326 plus or minus something. I've got the number over there, and it may be even more precise than that these days. Now, the real reason why this course is given and why this subject is so important is that the first question you should ask is, how is this possible? Because to make this prediction, this 10 seconds theory, we virtually didn't need any information whatsoever. All we used, in fact, was the up-down symmetry of the system. We said that t is an even function of m, and from that we deduced we deduced this result. So clearly something is very strange here, and the purpose of this course is to understand what that is. Now we're going to delve into that in huge detail, but I don't want to, I'm not going to spoil the surprise, but I do want to say there is one other assumption that we made. So can anybody here say, what do they think was the other assumption that we made when we made our 10-second theory of the phase transition? So go ahead. And by the way, when you answer questions, say your name so I learn your name. Some of them I know.
I'm Frank. And something about being able to write it as a Taylor expansion, like maybe something about the smoothness of it around the point.
Yes, exactly. So Frank said, we made an assumption about the smoothness that we could make a Taylor expansion. Well, what would be a more technical name for what the concept that you're just talking about?
That it's analytic.
That is analytic. So there's very good. So thank you. So this is we assumed something else, and what we assumed was that m of t is an analytic function. That assumption is wrong. Okay. In fact, phase transitions are where analyticity breaks down. So what I mean by that is, if I construct the partition function of the system as a function of variables like beta and h, maybe the number of particles, the volume, etc., this is the partition function is e to the minus beta times the Helmholtz free energy of the system, and this function is not analytic. At phase boundaries. When I say analytic, I literally mean not analytic in the sense of complex variables. Okay, and we will talk some more about that. Okay, so I don't want to go into further down that route. I want to now talk about scaling. So the next topic I want to present to you is scaling, and in particular the connection between scaling and a dimensional analysis. So what I want to show you is exactly how powerful dimensional analysis is, and then we're going to talk about the limitations of it and what we can and cannot learn from it. So let me give you an example just to show you, and then we'll talk about it in more general terms. So I'm going to talk about shallow water waves. So how many people here have done fluid mechanics? Okay, one person. Are you an engineer?
No.
Were you trained as an engineer?
Nope.
Nope. Okay, you're just well educated.
I just took it for fun.
You just took it for fun. Okay, we never make anybody take fluid mechanics these days, which is a shame because virtually everything. Well, never mind. I love fluid mechanics. So let's talk about shallow water waves. Now, the fact that most of you don't know anything about it is not an impediment for you to be able to make predictions about it. Okay, so let's see how we can get something from nothing. Okay, if you had to have a subtitle for this course, it's something from nothing. And in fact, when I gave a lecture in the American Physical Society March meeting, when I was awarded the APS Kazanov Prize, I called my lecture "Something from Nothing," or something from quote almost nothing. Okay, so let's just see how this works here. So here is the system. So we have a channel, and then there is some fluid, and it makes some wave. So it's a fluid. All fluids are blue, and the wave has some wavelength, which we can write down as lambda, and the wave propagates with some speed c. There's gravity pulling down here, and the height of the water if I look at the average height of the water, we'll call that h. Okay, so we're going to, so it's going to be shallow. We're going to neglect viscosity. And we're also going to neglect surface tension. So that all of those things can matter and can give you different sorts of waves, but we're just going to look at something different like this. And I'm going to tell you what the result is. So the question is, what is the speed of the wave? That's what we want to know. And I'll tell you what the answer is. The answer is that c squared is equal to g times the depth of the water, the h. And we could say that c scales like the square root of h. So that would be a scaling law. And we know that the scaling law has a regime of validity. So this we know is valid for shallow water. At least that's the claim. So excuse me, I'm still suffering from COVID, which I caught a month ago. So I apologize for that. So let's. I'm not infectious or anything like this. But let's talk about then where the scaling law comes from. So this would be an example of the scaling law. How do we know this? Well, in fact, the exact result I can write down, and that is the following: c squared. I'm going to write it down like this: g lambda over 2 pi hyperbolic tangent of 2 pi h over lambda. So that's a result that you can derive if you do know fluid mechanics. And now we can start to see how the result, the scaling law, arises. So the scaling law arises because we can do asymptotics on this. So we can say that if h is much less than lambda, then that's what we mean by shallow. Okay, so when we've talked about shallow, that means the water depth is not very big, but of course that's a meaningless statement for a physicist. Not very big with respect to what? The answer is not very big with respect to the wavelength of the wave. So when h is much less than lambda, then I can write down that c squared is equal to g lambda over 2 pi. And then I can do a Taylor expansion of the hyperbolic tangent. So I get 2 pi h over lambda, and then there's higher order terms. There's higher order terms of order h over lambda. In this case, they're actually cubed. They could be just squared. And so what that means is that then if I look at the lowest order terms, then what that then tells me is that c squared is g lambda over 2 pi times 2 pi h over lambda plus higher order terms, HOT, and that gives you the lambda cancels out, and I get g times h, and that's the result that I had told you before. Okay, so what I've just shown you is that when we talk about a scaling law, it's always valid in an asymptotic limit. You may not realize that, but it behooves you to find out what is the asymptotic limit that applies to the scaling law. Sometimes you'll see a scaling law, such as the energy spectrum of cosmic rays, that extends over, I don't know, many decades, 10 decades or something like this. And you say, well, it's just a power law. Okay, all power laws eventually end. Okay, all power laws have some regime of validity, and if you're going to show me a power law, you need to show me where it breaks down, both at the upper and lower length scales. So the scaling law is valid in an asymptotic limit, and when we looked at the magnetization as a function of t, going as t minus tc over tc to the power beta, that's true in the limit that t minus tc is much less than TC. Okay, so that was the scaling limit there. In other words, that T minus TC over TC tends to 0 from below. So that was true in phase transitions. It was true here. Okay, so that's an example of a scaling law. So now let's talk about how we might have obtained this result from dimensional analysis. So the dimensional analysis really starts with one basic law, and that is that a dimensionless quantity can only depend on other dimensionless quantities. So let's give you an example. Suppose I told you that y is equal to e to the x. So there's a relationship between two variables. Y goes to e to the x. Okay. So for this to be true, then x has to be dimensionless. Okay, because you can't have e to the 3 feet. Okay, you can have e to the 3, but you can't have e to the 3 feet. Okay, so it has to be dimensionless. Okay, so that's a basic law. Whenever you plot a graph on the horizontal axis, vertical axis. If you're doing this in any class of mine, and you'll say I'm plotting the height up on the vertical axis and the speed along the horizontal axis, or whatever it might be, that's not good enough. You have to say it's actually the height divided by 1 meter, the speed divided by 1 meter per second. That's the only way you can plot a scalar number on a graph. Whenever you're plotting a graph, you're plotting a scalar number, not a dimensionful quantity. So everything we talk about in physics are dimensionless quantities, and now we have to understand the rules for constructing them. And it's kind of like group theory. So let's go through how one does it. So let's talk then about the algorithm for dimensional analysis. So the algorithm goes like this. Step 1, take all your variables, and we'll do this in a minute for the water wave problem. Take all your variables, speed of the water wave, height of the water, gravity, whatever it might be. Take all your variables and form dimensionless groups from them. Okay, so let's call those dimensionless groups. Let's call those dimensionless groups pi. So we could say pi, pi 1, pi 2, and so on up to pi n. And I'm going to do this for you explicitly in a minute. So pi might be the thing that you want to know, like the pressure or the speed or whatever. And then pi 1 or pi 2 might be a dimensionless variable representing the height or representing gravity, whatever it might be. So we'll call them like that. And so this thing here is what you want to calculate. And then what dimensional analysis tells you, it says that it's just the statement that pi is some function of pi 1, pi 2, blah, 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 up to pi n. Now, That's all the dimensional analysis tells you. And you might say, but wait, aren't there many ways to construct these things? And the answer is yes, absolutely right. And we'll see that in a minute. Okay, so that's what dimensional analysis tells you. So let's give an example. So I've got speed. C is a function of gravity, the height of the water, the wavelength, and let's say the density of the fluid. Okay, why not? Okay, so that should be, those are the variables that the speed should depend upon. So let's now have a look at what the dimensions are of these objects. So I'll denote dimensions by these square brackets. So the dimension of the acceleration due to gravity, that's in units of length divided by time squared, meters per second per second. Okay, so that's what gravity is. The dimensions of h is equal to just length, whatever your dimension of length is, and that's also true for the dimension of the wavelength of the wave, lambda. The dimension of the density, that's mass per unit volume. So a mass per unit volume like so, and then the speed itself has dimensions of length times the -1. Okay, so those are the dimensionless variables that we have. So now let's see what dimensionless groups there are. So I'm going to say, well, why don't we make pi be defined as c over g h to the power 1/2. Okay, let's just check. So c is in length per unit time, g times h. So g is L t to the -2, g times h is L squared t to the -2. If I square root that, then I get L t to the -1. So c over gh to the half, this is dimensionless. Okay, so that's good. And then I can write down pi1. So let's define that. Well, that could be h over lambda. That's also dimensionless. And now you'll see that if we go back to density, there's the density. It has this m in it. Okay, over there. Nothing else has m in it. So m does not appear. So that means that there's no dimensionless group I can construct with rho, which means that rho cannot appear in this formula. Okay, so we've learned something already, and so so now what does dimensional analysis tell us? So dimensional analysis now tells us then that that pi must just be a function of the only dimensionless group that I can make, which is pi1, and so therefore c is equal to gh to the 1/2 times some function of h over lambda, and that is our general result from dimensional analysis. This is already very cool. We've already derived something which is beginning to look what we have over here, where I showed you the exact formula. Okay, now, it's not quite that, and we're going to see why in a minute, but we're clearly making progress. So now let's now the next step. So this was step 1, somewhere up here. That was step one. So now let's do step two. Well, actually, I'd say this is step one. So writing this down is step two. Okay, so let's now do step three. Step three is optional. And step three is take an asymptotic limit. So everything I've told you up to this box here, this is all the dimensional analysis tells you. Okay, that's the only thing dimensional analysis tells you. So step three is an extra one, and that is we're going to take an asymptotic limit. So let's do that in the following case, in the shallow water. So we're going to say that h over lambda is going to 0, i.e. h is much less than lambda, which is the shallow limit. And then you say, well, okay, h is much less than lambda. Let's say it's like 10 to the minus 17 or something like that. Well, that's just a small number. So I can therefore say that c is equal to g h to the 1/2 times whatever this function is evaluated at the origin. And that number f of 0 is just some constant. Say 3 or whatever. And so therefore, I can say that we have now derived our scaling law. C is scaling like the square root of h, or in particular, C is proportional to GH to the 1/2 power. Okay. So that's fantastic. Impressive. Question. Say your name first before you ask the question.
Serious? You could have written other.
Yes, I could. I'll come to that in just 30 seconds. Okay. Actually, maybe a bit, maybe 1 minute. Okay. But you're absolutely right to ask the question. We could have done this a different way and got a completely different result. And that's a very important point. I'm going to explain. I've deliberately done this to make you understand that there's something else that needs to be explained here. Okay. Any other question about this derivation? Okay. Does everybody buy it? Did we derive the scaling law? Apart from modulo the question that was just asked. What was your name again?
Serious.
Syria.
Serious.
Sirius. Yep. Sirius, right? Yep. So apart from the question that Sirius asked, which I'm going to come to, and there's a very good answer to that, do we derive the scaling law, right? Yeah. Everybody's happy? I want to make sure everybody understands before I go on. Okay. Okay. Wrong. I fooled you all. Okay. Okay. We made a very strong assumption. This strong assumption is critically important. It's a hidden assumption. Okay, it's a hidden assumption. It's so hidden that most people, even today, do not know that we have made this assumption. Most practicing physicists will do this argument and derive all sorts of interesting results, and they will not realize that they've made an assumption. Okay, so what is the assumption that we've made? We made the assumption that if I take the limit of pi1 goes to 0 of this function f of pi1, we've assumed that that is a regular limit. Now you might say, okay, look, okay, come on, we're physicists, we're not mathematicians, okay? This isn't a class in real analysis, okay? Okay, I mean, okay, yeah, some mathematician can go and prove this, okay? No, this is a physical assumption, okay? This is a physical assumption that we've made, and in fact, most of the time it's wrong, okay? And all the physical phenomena that are super interesting and super hard, the ones that we haven't solved yet or only recently solved, they're examples of where this assumption breaks down. This whole course is about problems where this assumption breaks down, where a very, very innocuous assumption breaks down, and it breaks down for reasons that are crazy. Okay. So we've assumed that, and it turns out in this problem it is correct. Okay, but in this course, now this breaking down here, this is obviously something to do with analyticity. Remember the first question that we talked about in today's lecture, the 10-second theory of phase transitions. Okay, we discovered that we'd made a mistake in doing that. We did the theory, we saw the result was completely wrong, and then I asked you why it was wrong, and we came to the realization that we made an extra assumption that we hadn't noticed, namely that there's an assumption of analyticity. And this is another kind of assumption, particular type of analytic assumption that we have made here. Okay, so we're going to talk about that in a few minutes. Now I want to get to Sirius's question. So the question that you asked, quite correctly, was about the uniqueness of the choice of dimensionless groups. So let's phrase that in a different way. Suppose we used lambda, not h, in our variable pi. Okay, so let's just go back here. Oh, I don't need to, there, it's always on the screen. So here's the variable pi over here. And that variable pi has the h in it. Suppose we'd used lambda. Could have done it. H and lambda have the same dimensions. So then what would we have got? So we would have got something like this. We would have got that c is equal to g lambda to the 1/2 times some function of h over lambda. But I'm going to write this function, I'm going to call it f tilde, so you don't think it's the same function as the one we had before, because it may be or may not be. We're going to see. Okay, so let's suppose that we'd follow this line of logic, we'd written this down, and now we said, okay, now let's take the limit as we take the shallow limit. So now we're going to say, now what happens in the shallow limit? So, well, we can answer that. So if we did what we said before, so we're going to take the limit as h over lambda goes to 0, just as before, and therefore that would predict c is equal to g lambda to the 1/2 times f tilde of 0. And that would say that the scaling law is the c goes like the square root of lambda. And that's the question that Sirius was asking. And the question is, wait, this seems right, but we actually know it's wrong. And the reason we know it's wrong is because I told you, here is the formula that you get from fluid mechanics. If you do the real fluid mechanics, you get this formula. And when you do the expansion, the asymptotic expansion, lambda cancels out and you just get h there. So we know that the correct answer is the one we got before, and it's not this one. Okay, it's not this. So what went wrong? So the answer is so no, this is wrong. We're sure of that because we know the exact result. So what went wrong? So what went wrong is that we assumed that the limit existed. And it doesn't. So the reason, why doesn't it? And the reason is this. It's a subtle reason. We're going to talk about this reason later on. But this will be the first time that you've seen this reason. This is not correct because what we would expect is that in the shallow limit, then we expect that the speed of the wave should not depend on lambda. And why is that? Well, if I take the depth fixed, then h going to h over lambda going to 0 means that lambda is going to infinity. So in other words, if I keep h equals fixed, then to get the shallow limit, I need to take lambda going to infinity. Now, if lambda goes to infinity, then we have a problem because you can see here that the speed will then go to infinity. So that would predict c would go to infinity. Now, maybe that's right, but what we know is that when we take a shallow wave, the wave exists and it's going at a regular speed. So this is not seen. And so what must happen is the only way to avoid this nonsense is that lambda cancels out. Okay. Now, how can lambda cancel out? Let's have a look. So basically, as I take the limit h over lambda goes to 0, and I've got c equals g lambda to the 1/2 times a function of h over lambda, f tilde over lambda, then as I take that limit, h equals fixed, lambda going to infinity, then we need that f tilde as a function of its argument must have a square root singularity. Why? If f goes like the square root of x, then what happens is h over lambda will go like the square root of h over lambda. The square root of lambda will cancel out the square root of lambda out in front, and then what I'm left with is the square root of h on top. So in other words, I can say f tilde of x must be going as x to the 1/2 times some other function, which I'll write as f of x in the limit as x goes to 0. And this function f of x is a different function. This function f of x is analytic and regular as x goes to 0. In other words, that means that f of 0 exists. So here's another notation for you. This means there exists. That's what this backwards e means. And before I told you this thing, that means because. So those are notations. Okay, so now just going back to finish the thought. So what this means then is if we apply this logic, then C goes as G lambda to the 1/2 times H over lambda to the 1/2 times some function f of 0, where f is now a regular at the origin, and so we get back GH as we had before. And so this argument that to avoid a impossible and ridiculous result, which is either 0 or infinity, but to get something that's finite, this argument is what I'm going to call a scaling argument. So we're going to say that this argument about deducing the asymptotics of what we can call scaling functions like this function that I introduced, f tilde of x, we'll call those things scaling functions. This argument, we will call this the scaling argument. And you've used it all your life, but you just didn't know it. Every example that you were given where dimensional analysis was used or a result could be obtained by dimensional analysis, you were tricked into it because the teacher showed it to you in the way so that it seemed like everything was going fine. There was no tricky arguments in there. So basically, what I want you to take away from this is the following. Take-home message is one, DA, dimensional analysis, tells you the functional form of the solution of a problem. And no more. That's point number one. And point number two, to get useful results, you need to make extra assumptions. Those extra assumptions about the asymptotics. So now let's categorize those assumptions. Okay, so it's not. This isn't to say that the type of argument that we use in dimensional analysis isn't important. It's just that we have to be very careful about the assumptions. In the first homework problem, I'm going to give you some examples. I'm going to change it from last year. I'm going to give you one example, which is to derive what is the main result in fluid turbulence. How many people here know about fluid turbulence? Okay, none of you do because you've never taken fluid mechanics, but you know it's swirly wordy things. Okay, and it's very unpleasant when you go through it in a plane. Okay, nevertheless, you are perfectly capable of deriving the most famous result in fluid turbulence using things that I've taught you, and I'll get you to do that in the first homework. So you need an extra assumption, and we're going to classify what those assumptions are. So let's go ahead and do that. And this first time that this was done, to my knowledge, was by Barenblatt and Zeldovich in 1972. And I'll give you some links to that in Teams. So the first assumption I'm going to make is type 1 asymptotics. You can call this common sense asymptotics. Common sense asymptotics says the following. If I've got some functional form, pi is f of pi 1, pi 2, pi 3, blah, 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 to pi n, and I take the limit as in the limit as pi 1 tends to 0, pi equals f of 0, pi 2, pi 3, and so on. And this is really good. Okay, it's a good thing to do. It's very important. Why is it important? It's important because it's reduced the number of variables in the problem. Okay. We saw that in the water waves. We discovered that from dimensional analysis alone, we could rule out the dependence on the density. Okay, so we know we only had one variable that we had to consider, and we knew already what the combination of variables was. So this is why it's a good thing. This is why engineers use this so much. Okay, so now let's talk about type 2 asymptotics. So type 2 is the breakdown of type 1, but in a special way. So we can think of what happens in type 1. Sometimes type 1 is sometimes called complete similarity. Why it's called similarity, we'll talk about a little bit later. That's sometimes called complete similarity, and type 2 is called incomplete similarity. And sometimes it's also called intermediate asymptotics of the second kind, or intermediate asymptotics of the first kind. Okay, so those are just names. So now let's go back to what is the special thing about it. Here is the special way that it can break down. Type 2 is this, that in the limit, as we take the limit, as pi 1 goes to 0 of pi, it goes like this. Pi 1 to the exponent alpha times some new function, let's call it f, of pi 2 over pi 1 to the alpha 2, pi 3 over pi 1 to the alpha 3, blah, 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 up to pi n over pi 1 to the alpha n. Okay, so that is a very particular way that this can break down. You might say, where would this ever come from? We'll talk about that and see where it comes from. So these are exponents, alpha, alpha 2, alpha 3, alpha n. So those are exponents. And you might say, well, what are these exponents? So there's two questions. Where did this come from? That's the first question. Another question is, what are the values of the exponents? So you might think to yourself, well, you know, we just saw in the first part of the lecture that I can deduce scaling laws, I can deduce power laws, I can deduce the power law of exponents by doing dimensional analysis. So why don't we just get these exponents by dimensional analysis? Well, the answer is no. And the reason we can't is because all the pi's are dimensionless. So we can't use dimensional analysis because nothing's got dimensions. So in fact, the only way to compute them is you have to solve the problem. And of course, that's bad news. That's hard. So we were doing dimensional analysis in order to avoid having to solve the problem. But now we've come to the conclusion that in some cases, in order to solve it, you actually have to solve the problem. Okay, that's bad news. Okay, well, you might say, well, okay, so who cares? And the answer of who cares is we do. Okay, because it is a class on phase transitions. And this phenomenon, this type 2 asymptotics, this is what happens in second order phase transitions. Okay, but suppose this was a class on fluid mechanics, we'd also care because this happens in turbulence. And suppose this was a class on shock waves in plasmas, I'd also have to care because this happens in those situations. And suppose this was a class on continuum mechanics and fracture in continuum, in solid state physics. We'd also have to understand this because this is what happens when you get a fracture in a material, when you get plastic flow. And suppose this was a course on quantum theory, okay, quantum mechanics. You also get this. You get all sorts of anomalous scaling laws that happen in when you do deep inelastic scattering of electrons from for example, from protons and so on, from hadrons. So in quantum field theory, in condensed matter physics, fluid mechanics, continuum mechanics, everything, you run into these problems. And whenever you run into these problems, okay, you either have to solve them, in which case then you become famous, or you can't solve them and they remain unsolved, and that defines the frontier of the subject. So this class is very important because it tells you about one of the most important examples where this phenomenon was understood. And it was understood only by a renormalization group. Okay, now, one of the things that you can say is, oh, well, if you can understand how it works in phase transitions, and this is the thing called the renormalization group, which Ken Wilson won the Nobel Prize for, well, maybe then we can use it to solve all those other problems, like the ones in turbulence or continuum mechanics or fracture and plasmas and so on and so forth. Okay, that's what I do. Okay, and that's what I did back 35 years ago. In fact, when I wrote my book, I showed exactly how one can use these techniques now to apply them to all these other problems, not just the ones in phase transitions, but in all these other areas, making that connection between quantum field theory and all these other problems in classical and quantum physics. Okay, so you can do that, and at the end of this quarter, I'll show you examples of how to do that. Okay, and it's in chapter 10 of my book, an introduction to that, but there's a lot more that was done since then. Okay, so we do because it's a class on phase transitions, but the same would be true also in high energy physics. So deep inelastic scattering. Turbulence. Fracture. Etc. 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 Okay. All right, so now let's talk about power laws in statistical mechanics. So before I do that, any questions? Listen. Okay, no questions. You all understood it perfectly. Yes. Say your name.
I'm Hadong, but you can call me
Hadong.
HD. It's better.
Hadong what?
Hadong, but you can call me HD if you want.
Hadong is fine.
Yes.
I won't remember it. I won't remember HD either, but eventually I'll remember it. Okay, head on the question.
So the question is like, we can say pi1 is, let's say, GH half,
Mhm.
but we can also call like pi1 is GH, like the O power,
Yes,
like,
yes, you can. Yes.
So
Yes, so you could have chosen pi, the other thing squared,
Yeah.
divided by, yes. And so of course, the thing is this, when you have these combinations,
Yeah.
you can multiply them together in different ways,
Yeah.
okay? Because they're all dimensionless.
I see. Is that related to the second type of the?
No, because, okay, I didn't tell you this. These exponents, these alphas and alpha twos and so on and so forth.
Yeah.
They turn out not to be like one or half or squared or something like that.
I see.
Okay, they turn out to be solutions of an eigenvalue problem, a nonlinear eigenvalue problem. Okay, and another way to calculate them is by using the approximation methods from renormalization groups, such as the epsilon expansion and things like this. So yeah, good point. So these exponents, these alphas, are often transcendental numbers. Sometimes you can write them down as nonlinear eigenvalues. They come about in a very specific way, and it's not easy to know how to calculate them. Okay. Okay. And we'll see how to calculate them in phase transitions. Okay. Any other questions? Okay. So
More question.
yes.
I just wanted to make sure-
Name?
Cindy.
Cindy.
I just want to make sure I understand the thought concept fully. So should we see the complete similarity situation as a special case where all of the exponents equal to zero when
Yeah,
goes to
yeah.
zero?
The complete similarity is a special case of the incomplete similarity. Yeah, yeah. I didn't mention another example of incomplete similarity occurs in electricity and magnetism. Okay, you'd think, how is it possible? You know everything about electric. How many of you people have done an E&M? You all had to do it because you can't graduate without taking it, right? Okay, okay. Did you ever run into this problem? No, no. Okay. Did you ever try to work out the capacitance or the electric field of a wedge? Okay, a conductor like this, but they're not like this, but they're like this in a wedge. Okay, did you do it? Really? What's the answer? I bet you didn't. Okay, what happens as you vary the angle of the wedge, there comes a critical angle where it goes from being type 1 asymptotics to type 2 asymptotics. And you can calculate that by renormalization group 2. Okay, it's insane. The same thing happens in fluid flow in a wedge geometry. What happens is that the flow is a continuous function of the angle until once you get beyond a certain point, the flow breaks down into an array of vortices circulating inside that wedge. And that phenomenon turns out to be exactly like the critical phenomena, but in space-time, of the formation of a black hole in Einstein's equations with general relativity. Even general relativity has this phenomenon. Everything has this. Okay. Okay. All right. So there's a lot to say about it. Okay, but I'm not going to. So you can talk about. You can find all these problems. I can help you find them when you do your term essay for this class. Write about these problems. They're fantastically interesting. And right. So let's go on to the next topic. remember what I promised you last time. At some point in this course, I'm going to explain to you how these power laws arise in statistical mechanics and how these power laws, the reason why they arise, completely undermined the whole way that we view the process of constructing physics and of constructing science. Okay, so all of that's going to come out of this seemingly innocuous background. Okay, now I want to make sure everybody's on the same page here. So let's talk about the phase diagram of most matter. Okay, so here is our phase diagram. I'm going to draw the phase diagram of matter in the pressure temperature plane. And so, so the question that we're going to do in this section is our goal is to see the phase diagram of simple matter. We're going to do something fairly basic, but we're going to see that there's something non-trivial in all of this. So let me draw the phase diagram in a sort of schematic way. So it looks like this. So this left line is going up to infinity. This right line is going to a point, and there are three phases of matter here. So let me put in one of those phases. So here's one of these phases. It's a phase that occurs at low temperatures and at high pressures. So this phase up here, we will call the solid phase. Okay. So what are the other phases? So what would be this phase down here, for example? This would be the gas phase, exactly. Gas phase is low pressure or high temperature. And then there's another phase in here, which is what phase? The liquid phase. Okay, so there's something odd about this phase diagram. So this phase diagram tells you that something interesting happens. So the first thing that's interesting is that there is a point here, which is called the triple point. And then there's another point on this diagram, which is, let's do it in purple, whatever this color is. This one is the so-called critical point. Okay, so the first shock that you might be you might be thinking about now that you're looking at this with fresh eyes is we talk about these as being phases, a phase diagram, but it's pretty obvious that liquid and gas are not different phases. Okay, so the first point is that the phase boundaries do not define the phases. So very roughly, here is P, here is T. So here's my phase boundary drawn as again. So you might say to yourself, okay, well, let's take a gas and let's increase the pressure. Okay, so what happens? So we start over here. Let's call this point, well, I don't know, whatever you want to call it. And we're going to go up like this, and we get to this point over here. Let's call this point A. Let's call this point B. And all I'm going to do is increase the pressure. I'm going to do it keeping the temperature fixed. And as I go through that, I will see the phase transition between a gas and a liquid. But there's something else that I could do. And we're going to talk about what you would see if you did this. I could start over here. I could go this way up to, say, this temperature. Let's call this point C. Then I could go up here to this point D. And then I could go down from this point D to this point B like this. So let's call this curve number 2, and let's call this curve number 1. And so you can see that the path of the curve 1 and curve 2 begin and end in the same places, but different phenomena are encountered. So let's. I want to talk about that in a little bit of detail. Okay. So let's see what we mean here. So let's draw a picture of what we would expect if we did curve number 1. Okay. So what I want you to imagine is that I start off with a container, and it has a piston in it, like so, and it's on some kind of device, a hot plate or a cold plate, that keeps it at constant temperature. So this is some sort of hot plate, let's say, or cold plate, whatever you want. So it's some device that takes temperature in and out, energy in and out, so the temperature stays constant. Okay, so then inside there, I want you to imagine that I've got a bunch of particles floating around. That's the gas. Okay, so now I want to ask what happens when we compress it. So now let's draw this picture again. So now I want you to imagine that I've compressed it. So here's now my piston. I've still got my heater, keeping it at constant temperature like this. And what do I expect is going to happen? Well, the readout of this experiment would be that I measure what is what is the pressure in the system as I reduce the volume. Okay, so let me put this over here. So this is page 16. So the readout is the pressure that I measure. So, and this pressure is measured as a function of the volume. Okay, so I'm reducing the volume of the system. So let's draw that graph over here. So that's the pressure. So what you would imagine then is that as I compress it, now the particles are banging into the walls. They're still at the same temperature, but now they're banging into the walls more often because there's less volume, and so the pressure is going to go up. So you would imagine that the pressure as a function of volume curve looks something like that. And if you remember the perfect gas law, PV equals NKT, you hold T constant, you hold N constant, then P goes like 1/V, and you get a curve that looks like this. Okay, so that's one of the outcomes that can happen. But another thing that could happen is that actually I'm at a lower temperature than the critical temperature. So the picture I've drawn here might be true for T greater than Tc. We'll say exactly what that is in a minute. But now let's suppose that I'm over here. And now what has happened is, as I've reduced the temperature, as I've reduced the pressure, actually I've now compressed it so much that some of the atoms run into each other, form little droplets, and those little droplets of liquid are heavier than the droplets of gas, and they fall to the bottom of the system. It rains. Okay, so I've got a gravitational field going down like that. And now what I have at the bottom here is I have some of the droplets has formed rain, and then the rest of it is just gas like that. So this now describes liquid-gas coexistence. So on this graph over here, what that means is I have actually got to this point up here. I'm just sitting on that coexistence line. And now what happens is as I keep pushing the piston down, all that happens is the proportion of gas to liquid changes, but the pressure doesn't. Instead of exerting more pressure as I compress it, all I do is I turn more gas molecules into liquid molecules, into high density molecules. So eventually I get to a state where, in fact, all of the fluid has now turned into liquid, and the piston is down over here. So now I've turned everything into liquid, and over here, everything is in the gas phase. So let's have a look at then at what happens. Once I've done that, well, what do we expect to happen then? So what I just told you is that over here, what I'm going to see is the following. First of all, I'm compressing the gas. So the volume, the pressure is going up. But then I get to this special point where now, as I compress the system, I make the volume smaller and smaller. All that happens is I am converting more gas molecules into liquid molecules, and the pressure doesn't change. And then eventually I get to this particular volume, and now I've got everything as liquid. And liquids are much harder to compress than gases. So the equation of state, the P as a function of V, is now going to go up with a much steeper amount like that. And so this volume here, so if I look at this, what does this tell us? So this over here is the gas phase. This over here is the liquid phase. And then this is liquid gas coexistence. Okay, and this is true, this picture is true when T is less than Tc. And so I could say, well, this is great. So depending on the temperature, I get these different curves. So now you could say, well, what happens if I take all these curves, and as I change the temperature, I'm going to see a bunch of curves which look like this. Let me do it like this. But they all have different places where this happens. So it'll go like that, and then maybe something like that, something like this. And so what I'm doing is in this direction, I'm raising the temperature. And I could join up these points here where the coexistence goes, and what I would get is a curve that looks something like that. And this thing here is the coexistence curve. So what I know is I'll add that coexistence curve, and I'm nearly finished. At that coexistence curve, there's two things that coexist. One is liquid and one is gas, and they have different densities. So I could plot this coexistence curve in the following way. What I would plot is the density, rho, and I would plot the temperature, T. And then what I've seen is that there's a critical temperature, and then below that critical temperature, let's say over here, there's two coexisting phases. One is the density of the gas, which is a low density. One is the density of the liquid, which is a high density. And now if I go to a different temperature, then this curve goes like that. And so this is really what we mean by the coexistence curve. The coexistence curve would be the density in the temperature plane, like so. Okay, so now you can say, well, let's end with another scaling law. So now you might say, well, if I look at this curve, it looks like that if I look at the rho liquid minus rho gas, so that's a number that clearly depends upon T minus Tc. So it's going to be something like this. What does it depend on? Let's call this quantity delta rho. And you can see that this delta rho goes to 0 above Tc. So this delta rho turns out, you might say, well, what does it depend on? So you might say, well, I know, this is just like what we did last time. This looks like a 11. So you should go like to the square root power. You might say. And this would be true as T tends to Tc. But no, that's not true. In fact, delta rho scales as T tends to Tc from below as Tc minus T to the power 0.327 plus or minus 0.006. Have you seen this number before somewhere? The answer is yes. You've seen it before. This was the same as the magnetization in a magnet. Okay, remember, that was the thing we started off. M as T goes to Tc from below, goes as Tc minus T to the power 0.32, I don't remember what the number was, 325 or something. Minus something like that. Whatever. Okay, it's the same number with an experimental error. Okay, so this is incredible, right? Here's a magnet. Just electronic spins, quantum mechanics on a lattice. And here is the liquid gas phase transition. Particles bouncing around, no magnetism, no lattice, nothing. And it behaves exactly the same way. Okay, and it's not, and this is not just, oh, it's a coincidence. It's really true. They behave the same way, and we actually understand the reasons for this. Okay, and you'll understand it too next time. So it is the same. This is an example of what's called universality. So next time we'll begin, we'll talk a little bit about what we mean by universality. There's two types of universality, and we'll talk about that, and we'll see how this comes about. Okay, so I will be sending out homework 1, which will be some exercises on scaling, and I will also be sending you out a sheet telling you how to get a grade A in this class. Okay, and how to do the homework assignments. Okay, so I'll be sending out a bunch of stuff. I'll send you those out by email. So check your emails. Okay, that's all for today.